I would like to thanks the organizer for this opportunity, and I will talk about separation of interacting active particle in a asymmetric channels. So let's have let's view this video. So here we can see the group of ships are moving in under confinement, and each ship can move independently, and their motion is impacted by their surrounding like fans, obstacles, and walls, and sometimes they are forming some bottleneck like structures. So the key point is their motion is affected by the confinement. So, and when we talk about the confinement, it comes from the boundary, and boundary may be flat and maybe undulating walls. So in case of 2D system, the walls can be undulating, and for that case, the cross-section area will changes, right? So for this type of geometrical feature, give rise to the concept called entropic transport. As cross-section area changes, the available phase space of the available for the particle will change. So, and this entropic transport is ubiquitous in nature, and there are real life example like geolite, ion channels, biological channels, and nanoporous materials. And there are artificial channels also. So, and they have an application in catalysis, osmosis, and particle separation. So here are some real life experimental realization of this type of systems, and they have shown that the entropic transport in the confined geometry, and this entropy, they have shown that the entropic transport in a confined geometry have greatly increased the diffusion of the particles. So keeping this thing in mind, we can ask, can we use this type of structure to separate particle depending upon the mass? So to model this type of system, consider the active Brownian particle shown as the red circle, and they are moving in this confined geometry. So it is a triangular asymmetric channel, so whose half width is given by this. So and when the active particle is moving in towards the boundary, it get reflect back within the channel, and there is a extra periodic force because so time dependent periodic force is acting on the particle. Because of that, that particle is moving forth and back along the channel direction. So dynamics is governed by the Langevin dynamics, and the random kicks experienced by the particle is modeled using the Gaussian white noise, and this is the inertial term, and this is the active force, and this n cap is the orientation vectors. So, and we are also assuming that the active particle is interacting with the neighbor particles. So here k is the strength of radius of interaction. And so what does it mean? Higher value of k means the particle is interacting with more number of particles. Because of that, the force is acting on the particular particle. So this is the oscillatory force, A is the amplitude, and omega is the frequency of oscillatory force. So what's we looking for? We are looking for the transport characteristic, and we are calculating average velocity along the channel direction and effective diffusion coefficient. So here are the results. So here it is the average velocity and d effective as a function of mass, and note that there is no interaction. So we can see there is a peak, the average velocity initially increases attending a peak, and then there is a decay. So we can clearly see the rectification of the particles, and we can we have a peak at mass m equal to 10. So for lower mass particle, in lower mass value, the viscous force is dominant over the oscillatory force, and in the higher mass region, the inertial force is dominated. That's why there is a decay in average velocity. But when we switch on the interaction, we can see an additional peak in the lower mass value in addition to the peak at moderate mass value. So as we are increasing the interaction strength, the rectification in the lower mass value is goes on increases as particle diffuses faster than the moderate mass values. And this inertial term, due to inertial term, this moderate mass values particle goes on, there is a decrease in the average velocity. So then we look for the oscillatory force. When there is a low, so here we are changing the frequency of oscillatory force, and we can see that when there is a low value of frequency, there is the peak height at the moderate value is goes on increasing. But as we are increasing the frequency value, this bimodal peak goes into the single peak. So and when there is no A equal to 0 means when there is no oscillatory force, even though we are getting a single peak in the low mass value because chosen symmetry of the channel. So because channel is asymmetric, that's why particle is moving towards the positive end side. And when we are increasing the amplitude, the moderate mass moderate mass particles goes on increasing value of average velocity. So here we see the effect of channel geometry. So we defined the aspect ratio. So W minimum and W maximum is half width of the maximum half width of the channel and minimum half width of the channel. So this epsilon equal to 1 corresponding to flat channel. And we can see that for flat channel, we are not getting any rectification. And for moderate value of epsilon, we are getting the bimodal pattern. So then we see the effect of self-propelled force. So here we can see that when we are increasing the self-propelled velocity, so this peak is lower mass value showing the higher rectification, and this bimodal pattern collapse into the single peak. So this is the final conclusion. When there is no interaction, we are getting this black curve, single peak. When we switch on the interaction, we are getting the bimodal pattern. So what does it mean? We can separate out particles depending upon the mass values. So these are the empirical relation that determine the position of mass values, and we can separate out particles depending by tuning these parameters. So this is the main idea. So this type of channel can be used to separate out the particle depending upon by tuning these parameters. So this is the articles and acknowledgement. Thank you.
Yeah. Hi, a very nice talk. Thank you. I just wanted to know the motivation behind choosing the inertial particle. So if you choose the inertial particle, how the dynamics will look like. If you choose the non-inertial, then uh, what difference will you see? Have you seen that also? I just wanted to know.
Uh, so so
Basically, motivation behind the inertial particle,
So,
choosing that.
we are looking for the colloidal particle which has certain mass. So that is the mechanism which we have motivated by to how to separate the particles like which have some range of masses. That is the motivation. But there are many studies which have overdamped Langevin equations all using this type of channels. So but our ideas is different. We want to separate out particle depending upon the mass, and people are have work on that. They have separate particle depending upon the size. So the idea is different in this case.
One more thing. In the beginning, in the movie, you show the ship, which is kind of polar kind of particles, right?
Yeah,
And then you are saying that showing the ABP kind of model, which
yeah,
is apolar.
yeah.
So I just did not understand the connection. Like,
So
I mean, why these ABP particles, how they will form a cluster? Will they form cluster, any kind of cluster in the confinement, or how they will move from one confinement to another confinement? That
yeah.
is my
So
question.
that video is for just for the analogy.
Yes.
Yeah, but I am coming to your question that what will happen when there is a clustering or not.
Yes.
That is the different study which one can perform in this type of structure, and there also are obstacles in that. If there is obstacles, then maybe there a clustering or trapping happens. That depend on the system.
Yeah,
So
yeah. It depends on the confinement width, how
yeah, so there are many parameters are there.
one can look at.
Yeah.
Okay, thank you.
Hey, hi. What happens to the particles when they come near the boundaries? Do they slide?
Yeah, they can slides, but their orientation vectors can change when they are moving towards the boundaries.
Okay, so did you look into the position distribution near the boundaries?
Yeah, we have look at that position distribution, and it is
Because there is a finite persistent time, right?
yeah.
For the
After some
orientation
time,
to,
they can when the orientation vector changes, it comes into
right,
inside the
that's why
channel.
I asked.
Yeah, so there are time scales we have to look for. After that, it comes back inside the channel.
Thanks.
Any more questions? Okay, if not, let's thank the speaker.